Hello, I'm Jinu Shin from KAIST, the session chair for track A. So first of all, thank you all of you for attending this exciting event. Korea AI Summit 2022 is being broadcast online, and you can watch the track you want on the official website. In the track A, we will have talks about efficient AI. So online audience, please access the QR code on the screen and leave your questions. Or you can click Q&A link in the YouTube description window and leave your questions. Okay, let's start the session. First, Professor Dimitris Pepeliopoulos from University of Wisconsin-Madison will talk about transformers as universal computers and prompt as their programs. So this is an online talk, and please understand that some network issue may occur during the talk. Dimitris, are you ready?
Yeah, I'm ready. All right, so thank you so much for inviting me. It's a great pleasure to be virtually here. I wish I could have made it over there. So this is joint work with some of my students and collaborators from the University of Wisconsin, but also Princeton University. So I want to talk to you a little bit about the architecture that a lot of people are talking about lately, which is the transformer architecture. And it's kind of an architecture that has literally transformed the machine learning world. In fact, a lot of the state-of-the-art models recently have been based on this architecture. So for example, in terms of language models, you've heard of potentially BERT or GPT-3, or I'm sure a lot of you have played with ChatGPT. All of those are based on transformer models. For image generation as well, Stable Diffusion, DALL-E 2, for image classification, VATs, they're all basically kind of like were born or are based on this attention is all you need type of paper, where it kind of like deviates quite a lot from what people have been using so far. For example, people have been using LSTMs for language models or convolutional networks for image classification, but somehow this architecture changed the landscape of what we can achieve in all these applications. The particular type of transformer model I will focus on in this talk is going to be language model type of transformers. So let me just start by, first understanding what is a language model. So, one of the things that the language model is supposed to do is it tries to infer kind of like the most likely next word in a sentence. So for example, my name is Dimitris and I am A. So what would be the most likely word to fill in the gap? The language model tries to, or is trained to figure out that word. So a language model is basically trying to model natural language so that it generates sentences that sound likely enough, all right? So in some way, it tries to build a probability distribution over sentences of words, all right? And the question is, how do people, I'm not an NLP person, I've only recently started, being very interested in large language models for the reasons I'll explain a little bit, but like from a high level perspective, if you'd like to understand how these models are trained, the idea is sort of simple. So you give it access to a really big training corpus, so training data in the form of text typically, that become tokenized, and then you train the tuning knobs and the tuning parameters of your model with the goal of building a joint distribution over words, and by essentially masking always kind of like the last word in a sentence. So for example, the thing that you're trying to maximize, you're trying to build a model that tries to maximize the conditional probability of the next word, given all the words that you've observed so far in a sentence, okay? There's been quite some excitement about large language models lately because, not just because of scale, but scale is perhaps one thing. So I'm sure a lot of you have heard the term large language model or an LLM. The reason why this like LLMs are a thing now is because, the reason why we call them large is because the number of parameters has sort of like exploded the past few years. For example, there's 500 billion parameter models out there, which of course you can't really train, but with some of them you can play. For example, if you've played with ChatGPT, this is, we don't know exactly what it is, but it definitely has hundreds of billions of parameters, okay? So the paper that sort of really made things quite interesting for me is the paper that kind of introduced GPT-3, if you've heard about the model. And the title of the paper is Language Models Are Few-Shot Learners. And this was a collaborative paper by OpenAI. And this paper, so the quite interesting thing is that it wasn't so much about how GPT-3 performs really well on like language tasks, but somehow how it also performs well on tasks that it hasn't really been trained on. Before we go there, I just want to talk a little bit about the scale of this model. So since this is the efficient part of AI or the efficient AI track. So what I'm sharing here is basically the plot from one of the plots from their paper, which basically compares all the different language models up to that time, or sort of like, the state-of-the-art large language models up to that time, versus kind of like the training time or sort of like, how long did it take to train them, right? And they had an interesting measure of computational cost, which was basically, petaflops per day somehow, right? So the way that they measure this is kind of like almost like kilowatts per hour. So like how many, petaflops per day do I need to train a large model? And for a comparison, I think what's useful to maybe think about is the following. So let's say, I'm sure many of you have trained resonance, right, or convolutional networks. So let's say that it takes you to train one of the biggest of resonance, or resonance 151. Let's say it takes us, I don't know, like a single day to train, right? So to train resonance 151 on ImageNet on a single day, it's actually, you need a few GPUs, right? With that amount of compute power, like if you're able to train resonance 151 in a day, you would basically need 100 years to train GPT-3. So the scale of compute that is needed to train those models is absolutely huge, right? So it's something that we haven't seen up to, the kind of like introduction of large language models. And the question is like, why does it take so long? So first of all, the model is huge, so it's 175 billion parameters. But the training data is also quite huge as well. So basically, this is kind of like, the data sets used to train GPT-3. And among the data sets is the common crawl, which is literally the entire internet, okay? So like basically everything that's in the form of a text on the internet has been used to train this insanely large model, all right? So the scale of both the training resources and the data used for that model is quite large. And every time that you kind of like, if you want to think about like, what are all these, like, ChatGPT and GPT-3, what are they trained on? Basically, literally everything that exists online, that's what they've been trained on, right? The way again that they trained this is sort of this idea of sort of maximizing the probability of the next word in a sentence. So the objective is kind of like the next word prediction, and it's typically autoregressive, which means that like you have a corpus of a bunch of sentences or like a number of tokens, and then it's kind of like autoregressive, which means that the loss is applied on all prefixes of a given sentence. All right. What is surprising is not that it does well on kind of like language tasks, on like, next word prediction. For me, what's very surprising and kind of like the whole premise of this paper is that it does well on stuff that are not kind of like beyond next word prediction. And this is the discussion about the emergent properties that happen at scale with these large language models. So there's one emergent property that I think is quite interesting, and there's been a lot of sort of excitement in the LLM community and in general in machine learning, which is what is now popularly referred to as in-context learning. All right, so I would like to explain to you a little bit in the next few slides what in-context learning is. I'm going to borrow the figures from the paper that we're discussing right now. So they have this nice figure, basically giving a few examples. So now there's no training. So you have GPT-3 and you're writing stuff, right? So this is kind of like the prompt. So you can like feed it a bunch of examples of addition, right? So 5 plus 8 is 13, 7 plus 2 is 9, a bunch of examples. And then you ask it, what is n plus 8 equal to, all right? And then the model, which is an expert prediction, is going to predict that the right thing to put in the question mark is 17, all right? Now, this is surprising. The reason why this is surprising that this model is not trained on addition, right? So addition is not one of the predictive or algorithmic tasks that this model has been trained on, but this property that it has, this capability that it has, sort of emerges precisely because of scale of the model, but also the data that has been trained on. Another example is fixing typos. So for example, there's all these examples of words that have a small typo, and on the right-hand side is the correction of that typo. And at the end, you give it an example. So after the sort of like the training, if you will, examples, you give it an example and you ask, okay, if I have CMIHP, what's the right word, right? And the completion is chimp, right? So it's kind of like the right thing. So it basically does sort of, it fixes typos as well, which again, this is not a task that has been trained on. This is not kind of like an autocorrect type of a model, but somehow it learns how to do autocorrect by seeing a few examples. Another example, of course, is translation. So these models, again, they're not translation models, but you have a few words, let's say, between English and Greek, or English and Korean, or any sort of almost any language pair that you like, you give a few examples of sort of tuples of words from one language to the other, and then at the end you ask it, what is the French for bread, and then it sort of figures out the right word, right? So the reason why this is called in context is because it kind of happens during inference. So the weights of the model are not changed during this inference call, right? So you have this big black box that you give in like these texts that I showed you, and then at the end it spits out kind of like the correct thing that like, perhaps another model that's trained on just that would do, right? So, so in context learning is the capability of the large language model to learn somehow to perform a new task at inference time through a few examples. And again, to me as a machine learning sort of theorist and practitioner, it's really, really bizarre that without changing the weights of the model, it can learn to do stuff at inference time, right? So the question is, how do I instruct transformer models to do what I want? So like, there were a few examples of how do I instruct them to like do addition, and how do I instruct them to do translation, but like, is there a principled way? And there sort of is kind of like a study of this. So this is basically called prompt engineering. Perhaps you've heard about it, which is kind of like the idea of how do I massage the input? How do I create an input for my inference call so that the model performs exactly what I would like to do? So if I want, for example, my model to correctly do addition of, let's say, 2 floating point numbers, what is the sort of like right set of instructions that I have to put in the prompt so that somehow the model understands or responds to it by doing the thing I'm instructing it to do? And this is not a straightforward thing to do. So for the things that we saw, it's kind of like obvious how to do it, but there's other more complicated, perhaps predictive or algorithmic tasks that we'd like to instruct it to do, that you have to be sort of specific, or even kind of like training or designing the prompts in a much more principled way if you want the model to kind of like do exactly what you want it to do. So the interesting thing though is, so there's kind of like, in this paper again, so this figure is from the language models are few-shot learners paper, where they said, okay, so let's have kind of like the instruction of what you should do. So like, for example, you can say, the following examples are example of additions, and what they would like you to do at the end is add 2 numbers, and then a bunch of examples, and then at the end you kind of ask it what is 1 plus 2. So the instruction, the prompt at the beginning, whether you include it or not, seems to make a big difference in the accuracy with regards to those in context tasks. So they saw, for example, that first of all, more parameters help and more data help, but prompt, like instructing the model to do stuff in, like, not just giving examples of addition, but explaining perhaps even the algorithm of addition, helps a lot. Okay, so the idea of the prompt is to explain somehow in single steps, if you will, or single instructions, the task that it needs to do, and then you give it a few examples. And when you have no prompt in this figure, it means that there's no instruction at all. You just give the examples. And prompting matters a lot. So it seems to be helping a lot to kind of like prescribe or give instructions to the model, which is, again, one of those things that have like really, those observations that, have, made us really excited about these models. I guess the other thing that makes us excited about these models is you can actually go and play, like, you can literally go now on ChatGPT and like, try all those examples and they work out. And if I had more time, I would be, I would go into that a little bit more. But so what I would like now to convince you is that in-context learning is useful, all right? So it's practically useful. And again, it's surprising. So the reason why I think it's useful is because, again, without fine-tuning, the model can be instructed to do stuff, all right? So kind of like you have a frozen model. You don't play with the weights of the model at all, but you can instruct it to do something specific. And for that reason, it is much cheaper than fine-tuning because it's kind of like comparing a single inference call with multiple backpropagation sort of rounds if you would like to fine-tune the model to do a particular task. So somehow, if we were able to magically force these frozen models to do all these algorithmic and predictive tasks that we want them to do without fine-tuning, that would be amazing, right? So that's why it's worth understanding the, in-context learning more. And I think it's very surprising because the model is trained on text data, right? So these results are from models that are trained on text data. So the text data, of course, maybe there's examples of addition, right? So there's certainly like a ton of examples of addition, but somehow the model knows how to do it if you give it a few examples. It knows how to generalize beyond what it has seen. And there's a lot of other non-language tasks that it can do. So it can do code translation, it can do reasoning, you can give it like a piece of code and you can tell it, you can instruct it, explain me what the code does on every line, and it can do all these things. And these are so far beyond the objective that you trained it on. And that is extremely surprising. The interesting thing though is the following. So these models, they do well on somehow like in distribution, if you will. So kind of like they do very well if the example, so if you give a few examples in context, let's say I want to do addition, and I want to test whether the model learned addition, and I kind of like try numbers similar to the ones I gave. For example, if I only gave integers, I tried on integers. So if I only gave numbers between -1 and 1, at sort of like, the test sort of example, I try, numbers between -1 and 1. However, if you go beyond those numbers, the models sometimes fail. So here's something so what I'm showing here is the following. So now it's not GPT-3, it's GPT-2 that is actually in fact trained to do one thing. So what this model is trained to do is it's trained to learn in context how to multiply arbitrary numbers between -10 and 10. So like any number, if you will, between -10 and 10 with 0.5, right? So basically you give it 10 and 5, 2 and 1, and so on and so forth. And at the end, you ask it, 4 question mark, what's the right answer? The right answer is 2. So like the only thing that it learns is multiplication by 0.5. So what we do is that because this is kind of like a very low dimensional type of a problem, you can actually plot all possible answers that GPT-2 would give you when you try to like in context teach it sort of like this type of multiplication. And what we see is that although it does really well on kind of like the examples, the few sort of examples that we gave it, it does really poorly outside of it. So like kind of like the out of distribution performance is not really well. It's this as a phenomenon is very interesting to understand because whatever implicit bias exists in like more traditional models, we don't really see it here in the way that we would see it in, let's say, a fully connected network, where perhaps the fitting line would be like a linear line rather than this bizarre curve that we see here. But the main question that I would like to, or like, what this motivates me to think about is, well, okay, if I want my model to do addition, perhaps it is possible to design it, to program it, so that it responds exactly to instructions of addition, rather than having to teach it in context, or even sort of like, fine-tuning to do this kind of operation. So this is the question I would like to understand. I would like to understand whether transformers and attention models can be programmed to do specific algorithmic things. So this is kind of like an interesting model and architecture, architecture and prompt co-design space, where you want to train or you want to design your model that it responds precisely to a given prompt. And you also have to sort of start thinking about, how do I design also the prompt as well? So there's kind of like perhaps two sets of parameters. So there's the weights of the model that you have to design, but also the prompt or the instruction that you give it. It's kind of like, for a given frozen transformer, what's the best prompt I have to give to it so that it returns to me the desired result? And through that sort of co-design, we started thinking about what algorithms can a transformer model learn to emulate at inference time. And there's actually very little work in this space, and sort of like this idea of hard coding stuff, or like building transformers to do specific things. So what I will try to do now is not kind of like train transformers. I will try to literally hard code the weights to do a specific algorithmic thing. So there's a few things that actually we know in this space. So one thing that we know is that transformers and attention models are universal sequence maps. So what this means is that if I have a sequence of words and I want to sort of like create a function f that maps that sequence to a completely different sequence, then there always exists a large enough transformer that can essentially emulate that sequence to sequence function. Unfortunately, to sort of like, give such a strong result, you also need exponential size transformers. So you basically need really, really large depth and width. There's another interesting sort of line of work that basically characterizes the expressive power, again, of transformers, but from a more computational perspective. There's a couple of papers that prove that transformers are Turing complete, which means that they can recognize, you can build transformers that they can recognize any language. The downside of those more theoretical results is that they typically either require extremely large networks, or they're generic constructions that they don't really apply to particular algorithmic tasks that you may care about. For example, just like adding two numbers, or like doing some sort of algebraic computation on your inputs. The sort of like the path I would like to take is I would like to understand, how can I build a transformer that it almost acts as a parser for the prompt, right? So I want to do kind of like a much more sort of like perhaps programming languages approach to like designing transformers. So this, again, doesn't have to do with training. It's about literally building Lego blocks that at the end will essentially give me a desired algorithmic outcome. What I will try to convince you is that this is actually possible, and we have explicit ways of essentially building explicit transformers that actually do a bunch of interesting things. So I'll try to convince you about those in the next few slides. So the idea again is that transformers, like what we realize is that they're programmable. So unlike traditional architectures, like, I don't know, like fully connected networks or LSTMs, you can actually somehow figure out the set of weights in a transformer so that it emulates programs. And that's actually quite a strong concept, because you can do a lot of cute things, as I will show you. So there's a few things that I started thinking about, like, once kind of like, went down this rabbit hole, I was like, there was, a bunch of discussions about this on Twitter. It's like, is it possible, when I want to do addition, right? So when GPT-3 does, we want to do addition, why do we have to train it to addition? Or like, why do we have to kind of like, doing context learning for it to sort of like figure out how to do addition? Could it use like, a calculator, right? Or could we come up with a GPT-3 that also acts as a calculator? Can we create transformers that emulate learning algorithms, right? So like that in context sort of learning that it happens, can you make it so that it does much more than that? And then at the end of the day, is it possible to create a transformer that literally parses commands and outputs what, like, basically a universal computer would output. Okay, and the answer to all these questions is basically you can do this. And the reason why this is possible is that, again, because unlike traditional architectures, transformers, they have sort of like this flexibility of, you design you sort of co-design the prompt, like, the input and the weights in the network. All right. So the way that these constructions typically work, or the way that we build it, is by kind of like figuring out small Lego brick components that we will eventually put together to build actual stuff. So the first thing that we design, or the first thing that we figured out, is that you can build. By the way, every time I say build a transformer, this is like, a couple of layers of attention. It's not like 100 layers with like a billion width. It's like, literally 5 layers of attention or something like that, even less than that in many cases. So we can build transformers that do lexicographic operations. This was sort of known from other works, but basically, if your input is sentences, but let's say it's kind of like these shapes now. So what you can do is like take that input and you can build a transformer that does arbitrary things, like, copy, move, delete any of those blocks in any part of the input, right? And the way that you do copy, move, and delete is prescribed in the input itself, right? So this is Lego brick number 1. You can do lexicographic operations, which basically means whatever you give at an input, you can basically do whatever copy, move, and paste you would like to it, all right? The second thing that is actually quite surprising is that you can evaluate arbitrary functions, and this was not known before. So basically, the softmax can simulate somehow universal approximator for any function that you like. So forget about the technical details. The main thing is that a single layer of attention can implement any function that you like. And there's sort of like a technical discussion behind it, but we don't have time to go there. But just sort of understand that, like, you have, let's say f of x is a neural network, or f of x is like an algebraic function, or it's a polynomial. A single attention layer can sort of create that f of x for you if x is given as an input. And now we go to like Lego bricks 3, 4, and 5, which I think are the more interesting one, the more sort of like programmability aspects of it, which is, first of all, you can predefine a set of functions that are hard-coded inside the attention. And in the input, you can say, I want to evaluate x on the ith function that I have predefined and have hard-coded inside the attention, right? So you can choose from a predefined set of functions what you want to evaluate. Lego brick number 4, and this is kind of like the coolest thing. So it took me back to like, my assembly years. So you can maintain a program counter. So you can have in your X input something that operates as a program counter, and you can have like, essentially a constant number of attention layers, again, whatever, 5 or something like that, that basically what they do is they say you were at line 1 of your prompt, now you're going to go at line 3 of your prompt, right? So you can keep track of what basically prompt you're executing. And the last thing, which is also perhaps quite cute, is that you can implement a conditional branch, all right? So what is a conditional branch? You have your nice program counter, and then at some point you say, if a condition is true, set that program counter to another thing. So what this allows you to do is you can arbitrarily jump to any command, or if you will, any line of your prompt, okay? And these 5 Lego blocks basically allow you to do whatever you want. Again, these Lego blocks are complete, like they're explicit. They have like, it's not an existence result. I can give you a set of weights that actually do exactly what I promise you that they're doing. And you can build interesting things. So what can you build with this? So first of all, I guess before, like there's 3 examples, but the idea is that like you have to, now we go to the idea of designing the prompt. So the way that the prompt typically looks is that you're going to have your commands, like what you want to do on your variables, and you have a scratch pad that operates as internal state and memory for the attention layers to do stuff during the process. And there's a bunch of metadata that are kind of like important for the technical part of it, but you don't have to like worry too much about it. Again, the interesting part about these transformers is that they're basically pretty efficient, so they're very small. And here's things we can do. So we can build a calculator. We can explicitly build a calculator that does addition, multiplication, square roots, cosines, whatever you want. And the prompt is basically the equivalent of add X and Y, and the output is exactly X and Y for every single X and Y, all right? So it's not kind of like the thing where you have this issue of like bad extrapolation. This is always the right result. You can build a learning algorithm. So you can give as input, so the way that you design the prompt now is your training set, your test data, your loss function, the transformer is like, again, a bunch of like a constant, set of layers that essentially emulates SGD on the training data and the loss function and evaluates the predictor on the test data that you give to it. Okay, so again, you kind of like implement a learning algorithm or emulate a learning algorithm through a fixed or a constant set of attention layers. And the last thing we can actually build is, in fact, a computer. So you can build computers with transformers, right? And this is, again, an explicit sort of like construction. Again, I don't have time to go into it, but we're going to soon basically release GitHub code where, you can basically play with all these things. I know that I'm running out of time, so I just want to conclude that what I think this means for large language models is that, they're not just trainable, but they're also very programmable. They can emulate compute boxes, calculators, learners, computers, basically. You can think of them in this context that prompts are the programs. And for all of those, there's actually explicit, weights and explicit constructions that they do all that. So there's a major interesting open questions, I think. The main thing I'm interested about is like understanding how to fuse this with existing large language models. So how can I combine GPT-3 with a calculator transformer? Whether we can use these models to basically distill those tasks, use them as teachers for distilling those tasks. So I'm kind of out of time, so I'm gonna basically skip this too, but perhaps what this made me think is that maybe the future of AI kind of looks like an interconnected web of transformers, because not only from the perspective of prediction they can do everything, but they can also be programmable to be computers. So with that, I will conclude, and I will be happy to take any questions.
Thank you, Dimitris, for your great talk. Now we are going to have Q&A session, so we have time for one quick question. So, okay.
Thank you for the great talk. So my question would be that you claimed that the transformer is a computer, and given your instruction set, it looks like it's Turing complete because you can jump back and you have branches. So that's basically what you need for a Turing complete machine. And now I'm struggling to understand how I would implement an endless loop with the transformer, because it really just runs through, and there is no way in a transformer to go back. So actually, it doesn't seem to make sense to me. So I think I see a proof that it couldn't work. So could you explain how it actually works?
So that's a great question. So what I skipped is the fact that like at the end of the transformer, you have one recurrent link. So basically the output, you pass it back in the input, right? So like when you build it or when you train it, it's just like a feed-forward transformer. But when you use it, think about it like, the same way that you use a CPU, right? So you don't build, like the size of a CPU is not proportional to the program you're running. You just like keep looping back, right? So basically you need the recurrent link that essentially feeds back the output of the transformer in the input. And at some point, there's like an end of file sort of, or like, end of whatever type of a command that just like spits out zeros after that. I hope that,
So it's really a transformer loop that is then emulating it's not a single transformer. I see. Okay, cool. Thank you.
Yeah.
Okay, thank you, Dimitris, for your talk again. Okay, so we are going to have next speaker. So next, Dr. Mostafa Denghani from Google Brain will talk about efficiency, the next grand challenge of artificial intelligence. Please give him a big round of applause.
All right. Thanks for the invite, and this is great to be here. I had a lot of fun talking to students, and hopefully we can have more chats in the afternoon. I wanted to talk about the efficiency and how the next big challenge in AI is going to be about efficiency. And I think it's already clear by now that why efficiency is important and why we need to talk about efficiency. First of all, scaling up is going to be a big part of moving forward in advancing AI. I think unless people in the inductive bias camp, they're going to come up with a brilliant idea that changes our mind, I think scaling is going to be one of the main directions. The other one is that if you make all these models efficient, it's going to enable us to do stuff with new application and use cases, and like on-device learning and federated learning, and there are plenty of applications that we can actually just go toward by making our models efficient. The other one is basically, we can democratize AI if we make things more efficient. We can, if we enable a single a student sitting in a lab working with a single GPU to do something awesome, it's going to maybe open up some new ideas, and that's actually already, contributing to the advancement of AI. So that's what I'm excited about. And the last one is that at the end of the day, we want to be we want to come up with some AI that is as intelligent as human. And one of the things that is super impressive about human is that it's super efficient. It's like in the morning, you take a bowl of cereal, and you are capable of doing all these amazing things during the day, and you don't need to consume the power of a city to be able to, solving a really complicated math problem. So today, I'm mostly covering 4 different things. One is about efficiency, different aspects of it, and some misnomers, which is basically a really short summary of a paper that we wrote. The other one, I'm going to talk about efficient transformers, because we talk about transformers, and maybe efficiency in transformers would be something to consider, especially in some applications we're working with long context, and efficiency becomes a concern. The other one is basically talking about smart allocation of compute and dynamic, adaptive and dynamic computation. And the last one is recycling, which I think is becoming a new trend in training larger scale models. So this is from a paper that we published on iClear 2022, and this is actually, I'm on this paper, but I want to, just give it a really good promotion that it's a must-read for people who are working on ideas around making models more efficient, because there are many, many mistakes and misnomers about efficiency that we discussed, and this is not this is mostly a collection of things and take-home messages that we grab from different projects at Google and outside Google, and there are many points that I would say important, and would be nice if you're working on efficiency. I really recommend actually reading through the paper, so starting from model efficiency, and when we talk about a method being efficient, first of all, it's important because it should be one of the axes that we compare different models together, and the reason is that it has a direct impact on the cost that we have, but the question is that what does that mean for a model to be efficient, and how do you quantify efficiency, and what should be considered as the metrics that we are evaluating efficiency with. And the other question that comes around all the time is that what is important, efficiency during training or during inference? Because this can somehow go against each other, and you should think about it. Okay, now if I want to make a choice about the design of the model, which one should I go for? There are many different cost indicators and metrics that people use. For example, total number of flops during training, or per example, forward pass. We have number of parameters, so people use number of parameters as a cost indicator. Speed, which is measured by throughput, latency, wall clock time, memory access cost, and different type of metrics. But there are also other metrics like sample efficiency, carbon footprint, the cost of training, number of model activation, memory consumption. So there are many different aspects that we can actually look into when we are talking about efficiency. I'm going to talk about the first 3 mostly, but there are also other stuff and experiments and analysis about the rest in the paper. So back to the question about which one is important, inference or training. So inference, it's clear, because we want to, at the end of the day, use these models on devices and during inference, which basically many believe that basically the cost of training is going to be amortized at the inference. So if you make a model inference efficient, it doesn't really matter how much cost you have during training. But this is a little bit maybe not correct, at this situation simply because these models are so huge that you can no longer just simply say that, oh, no, the cost of training is going to be amortized. It's really expensive to train a GPT-3 or you know, a larger scale model on any modality. So this is one thing. Another thing is that in many applications, you need to retrain your model like multiple times because you know the data changes or there are some you know, privacy concern and different things that basically requires you to train a model frequently. But what is the misnomer here? So misnomer here, if I want to summarize it in one sentence, is that in many situations, people just think that the cost indicators and cost metrics are correlated. So if we have more flops, we also have more parameters, and probably the speed is lower, and you know its latency is higher. But this is not correct. And in many situations and cases, you can see that there is a contradiction between these cost indicators. This is an example of 3 different transformer models. The first one is like, you know, vanilla transformer, or dark orange one. The second one is switch transformer, which is a sparse model. The last one is universal transformer, which has parameter sharing across layers. So if you check them, basically what I like about, you know, comparing models is that you need to always put them on a 2D plot where one is like, you know, measuring the cost and the other one measuring the quality. So if you do that, and as a cost metric, you put like, you know, number of parameters, you can see that, you know, universal transformer is amazing. It's on the Pareto frontier because it has less parameters and, you know, accuracy is, you know, fine. But if you just change the cost indicator and put flops, you immediately see that, you know, universal transformer sucks. But on the other hand, you know, like sparse models, they're amazing because, you know, with like a lot of parameters, they have some control over, you know, the number of active flops or you know, the parameter that they're engaging in each forward pass is like much less. And the other one is just basically the speed. So you can see that, you know, clearly in this example, you know, if you look at the parameters or if you look at flops, which model is better and which model is worse, and they're like different conclusions. Another thing that I wanted to also maybe talk about is that basically when you talk about training costs, and if you think about, you know, like how should I deal with training time, and if I need to consider it as something that is important, there's easy way to game with it. As an example, you know, this is like a plot here, and then I have a green, like, you know, there are 2 different models. One is like, you know, green, and the other one is red. And then at like, you know, 0.5 million steps, you can see that, you know, the one that is red is much better. But if you just continue the training, you're going to see that, you know, the red model has no chance to get to the accuracy or the quality of the green model. So if you just judge by, you know, like, you know, 0.5 million steps, green sucks. But, you know, and on the other hand, if you just, you know, go back one step and look at the complete picture, you're going to see that, you know, this is easy to game with the training time by just, you know, incomplete reporting of the metrics. Another example is this one. You know, again, there are many situations that you target one, you know, specific accuracy or quality of the model, and then you know, one model might shine over another one. But if you go to another accuracy which is higher, maybe the model that is shining never reaches that accuracy. So it's easy to actually game with the training time. So it's one of the misnomers that we actually highlighted in the paper. As I said, there are many situations where these different cost indicators can go against each other. For example, when we have parameter sharing, if we introduce a sparsity, if we have different type of parallelization. For example, if you have a model and then you scale it up by adding layers, it has different implication on the efficiency of the model compared to scaling up a model by increasing the width of the model. Because when you increase the width, you have more parallelization, but when you increase the number of layers, it's always sequential in operation. So you need to wait for the first layer to be able to run the second layer. At the end of the day, it really depends on the target platform, right? So if you are comparing 2 models, maybe on GPUs, one is better, on TPUs, the other one is better. If you go to CPUs, maybe completely different conclusions. So it would be nice to always consider all these assumptions and see which one is the one that we care about. One thing that I wanted to maybe basically like emphasize is that if you're comparing different models, and these models have different architectures. You know, for example, if you're comparing ResNet or convolution-based architectures with transformer-based architectures, it's easy again to be misled by looking at different parameters. So if you're looking at parameters, like number of parameters, you're going to see that, you know, for example, efficient net is really good. It's on the Pareto frontier again. But when you look at, you know, some other metrics, you know, like speed, you can see that, you know, it's no longer the best model. So depending on how these different models are different in terms of architecture or different assumptions, could be, you know, the conclusions that you're making out of these comparisons could be completely different. One thing that I noticed that most of the papers, when they do compare different models in terms of efficiency, there are two approaches. One is that they say, okay, you know, I have my baseline. It's a BERT with, you know, like base with 100 million parameters. So my model should be also the same size, you know, 100 million parameters. So they do parameter match comparison. Sometimes they do flops match or compute match comparison. So they say, I don't care how many parameters my model has compared to the baseline, but I just try to match the speed, right? So if baseline trains in 5 days using 2 TPUs or GPUs, maybe I should come up with a model that, or I should compare my model after 2 days of training on these 2 GPUs. And could be a bigger model, it could be a smaller model. So that's also a fair comparison, right? So which one is a good one? It really depends. And I think a good answer is that you should do both. You know, you should not really compare different models in terms of, you know, number of parameters. For example, if you are comparing two airplanes, you don't want to just, you know, compare them in terms of, you know, their weight, right? So maybe it's not it's a bit of off comparison if you just do that. So if I want to come up with like one concrete suggestion about like efficiency and reporting is that, first of all, do not go for a general efficiency claim. Never say that my model is efficient. You should say that in this situation, with these assumptions, on this hardware, and you know, like, so make all the assumptions, and they say, compared to this model, it's efficient, or it's a bit more efficient, right? So that could be more scientific than just saying that, oh, we have a model. I know, I mean, you can read on many papers abstract that, you know, we have an efficient model that, like, blah, blah. And this is a bit like, you know, non-scientific to basically claim general efficiency for a model. So going to the transformers, so like similar to the slide, the last slide of Dimitrios. So he had this slide that, you know, like many transformers connected to each other, and, you know, maybe the future of AI is transformers talking to transformers. So we used to have, you know, all these different architectures for different domains, like computer vision, natural language processing, speech translation. So we had, like, you know, convolution-based or LSTMs, and now everything is transformer. So that's where we are heading to, right? So we're converging to a single architecture, and I'm excited about, you know, just basically the time that we put out the vision transformer, we had no idea this is going to take over the whole field, right? No, it's crazy that, like in computer vision, everyone is using vision transformer, and this was also shocking for ourselves, you know, because you know, this some architecture coming and taking over computer vision and like, you know, reinforcement learning and speech and everything is strange in a short period of time, but also exciting. Because it opens the door toward many ideas, like, you know, having a universal model. So transformer architecture, I don't want to go through the details, but it has a block. It has, like, every layer has 2 blocks. One is self-attention, and one is preposition feed-forward, right? And the self-attention one has basically some sort of, you know, a cross-sequence shuffling of the data. And one thing that is important is that this part of transformer architecture has quadratic complexity. So when you have a sequence length of n fitting to a transformer, at every self-attention layer, you have the cost of ON2, and that could be problematic when you go to longer sequences. And I think that is one of the situations where transformers are going to become expensive. Think about like, videos or, really, really long context. Imagine that you have a model and you want to apply it on summarizing a book, right? So, and this book, so the input length is huge. And with this quadratic complexity, this is going to take ages to get like, the summary of the book out of your model. So we had this efficient transformer survey, which we published like, I don't know, 2-3 years ago. And we started with this taxonomy. It actually, like, we updated that, so many new models. So there are different ideas exploring the, like how we can tackle the quadratic complexity of the self-attention. And we tried to somehow group them in, these 5-6 groups. One of them is just, recurrence. Maybe we can somehow add some sort of recurrence to the model to, instead of basically consuming the whole sequence, which is pretty long, as a single input, we do that recurrently, similar to RNNs, for example, Transformer XL. There are some ideas that they say, if you have a really large input, maybe you want to use some sort of memory or some sort of downsampling. Sometimes you have some ideas. They are actually thinking about using some sort of fixed or factorized random patterns to work with part of the input instead of actually applying the whole whole self-attention on the whole input, especially when it gets long. There are ideas that they say, okay, instead of actually working on doing something with, making the model more efficient, maybe we can rewrite the self-attention to avoid the quadratic complexity. And these low-rank kernel ideas, they are basically thinking about a linear version of this shuffling of information that self-attention does. And there are also other ideas around, sparsity or learnable patterns. So I don't want to spend time on this, but if you had time, just, and if you're interested, I actually had a chat with one of the students, and they told me that they're working with Longformer, which I think it's probably somewhere sitting in this context. And I think that there's going to be a challenge about long context soon when we basically push transformers to applications that we are supposed to work with larger inputs. We also have a benchmark, we call it long-range arena, where we compare different models across different tasks, where these tasks were designed to basically measure the ability of transformers for capturing the long-range dependencies, but also with respect to their efficiency. So we have, they have this LROI score, which is the average across multiple tasks that, they evaluate transformer on different tasks where the transformer is exposed to sequences of 4K tokens, so pretty long. And on the other axis, we have a speed, and then we compare a bunch of transformers. This is from 2020, I think, but there has been a lot of new ideas, and this is a really incomplete picture. So we had, we are amazed by the progress in this direction, and there are many, many new ideas coming out that make transformer much more efficient than the vanilla one. All right, okay, so talking about a smart allocation of compute, which is slightly also relevant to the talk of Joe and Thorsten from yesterday. So one thing that is quite interesting and important is that one of the most important things that makes human brain scalable is that it's really good at allocation of compute and power. So we know that how much energy and time and thinking should we do for dealing with different problems. When I just talk about something and something going on in background, I know that I should spend less energy and time on consuming or processing that, and more on the conversation. But this is not necessarily the case for the models that we have today, right? And there are many reasons, and some of them are basically technical reasons. For example, some sort of dense or uniform allocation of compute helps easier training. The other one is that basically it's, like I'm going to talk about it a little bit like more, but the hardwares that we have, they're not necessarily the best hardware to support the idea of having some sort of smarter allocation of compute or dynamic allocation of compute. But thinking about that direction, I think it's important simply because at the end of the day, we don't want to have models that they spend similar amount of compute on different inputs, right? I want to start with some examples and say that, basically, one of the things that is important, in the context of, for example, computer vision, most of the models that we have, they are designed to process the images as a grid of pixels, right? So they sweep over all the images and they say, okay, I want to process the first patch and then the second patch and so on and so forth. But the point is that as a human, I don't do that, right? Like I don't spend, or let me actually go to this example. So if I want to watch and process this image, I don't spend as much as time that I spend on the bottom half to the to the top half, right? So this region 1, basically there's almost nothing there. It's sky and some clouds. So so what I do is I immediately focus on the part that has more information. But again, I have some sort of control over that. For example, this region 3, there are a lot of things there. There are a lot of details about these tree leaves. But again, I don't get lost in that details, right? So I'm able to basically narrow it down to the part of the input that is important for me, and just skip spending, I don't know, my brain on parts that are not really critical to understand the input. But this is not the case for like most of the models that we are working with, right? Now, if you work with convolutions or universal, the vision transformer, they just process these like inputs and allocate similar and uniform amount of compute to different parts. Another good example is video, right? Like on videos, if you have this video, which is basically I think it's from Epic Kitchen dataset. So it has a camera that captures what is going on on the kitchen sink, and if in many of the models that they are actually processing the video, they are repeating the computation for parts that doesn't change across different frames, right? Like for example, if you're like looking at the stove here on the left, this stove doesn't change across frames, but if you're working with some sort of model that processes the video, every time that model sees that pixels that describe the stoves, spends similar amount of compute. So it doesn't know that, oh, I already spent some compute to understand what's going on 3 frames ago. Similar to that one, like sequence processing. So like if you're working with transformers for sequence processing, right now, it just depends on the number of tokens, right? I mean, if you have a really complicated sequence on the bottom and the simpler one on the top, most likely, the amount of compute that you're spending on this is pretty similar. And it's not like, oh, we have more time spending on processing the bottom one simply because it has some sort of nested architecture structure. But human is not like that. I spend more time on processing the bottom one compared to the top one. So there are, this is like a really incomplete grouping of the ideas, but it just helped me better understand what's going on. So around dynamic allocation of compute, there are, I would say there are two main set of ideas. One is basically those that they work with the input. So they say that, okay, I might be able to massage the input in a way that it is a bit less uniform. For example, in this example, maybe I can make a single token out of the top part, and all the other tokens in the sequence goes to the bottom part, right? So basically, the tokenization on the input goes in a way that is not uniform anymore. The other one is that basically ideas that they go to the model, right? So that the input goes to the model, and the model decides that how much compute I want to spend on this part of the input and how much compute on the other part of the input. So, so this like, basic ideas that we apply on the input, sometimes we apply them on the raw input, like that basically before even fitting to the model. And the other one is basically, on the intermediate representations. And On the other hand, those that they go to the model, sometimes, we have dynamic number of steps, like these ideas that they say, okay, I have basically a CD or PonderNet or universal transformer. They have different number of processing steps for different inputs, depending on the complexity of the input. And, or any type of sparsity, mixture of experts. So basically those ideas, they decide on what type of experts should be used for processing this input. And right now, most of the mixture of expert models, they focus on experts that they look similar, but we are maybe moving toward having different type of experts. One is more complicated, and one is more simple. The last one is basically dynamic allocation of compute across tasks, which is the idea of pathways, which is actually one of the biggest projects at Google. So back to the transformers, because again, we're talking about transformers these days. I wanted to basically discuss this idea in the context of transformers. So in order to have different processing time for different inputs, one idea is that what if I have some sort of mechanism in the model that has that enables different number of computational steps per input, and this could be like this idea that the universal transformer uses. So we have an input of, let's say, 4 tokens, and the last one is the simplest one. So what it does, it says that after 2 layers, I want to halt, and then I just use the output of layer 2 for this token because it's just like a dot at the end of the sentence. I don't need to spend too much processing on this token, and the position number 2 is the most complicated token, or at least the complicated part of the input. So I need to spend more processing on it. So we have variable number of computational steps per token, but you can also think about having similar number of computation across tokens, but different across examples. Like for input number 1, I run the model for 2 layers, and for input number 10, which is more complicated, I run the model for 12 layers. This confident adaptive language modeling is also a new paper from our group that basically what it does, it says during decoding, maybe I can basically autoregressive decoding, maybe I can enable having different number of layers per token. But one thing that this is not yet so hopefully this paper is going to go out soon in next week or something. But this is an idea that we explored, and I really like it simply because it just removes a lot of complications from implementation of dynamic computation in transformers, and we call it adaptive tape. And if I want to basically give you a little bit of some sort of compare it with something that in your daily life, is that there should be we have two things in each model. One is that the size of parameters of the model, and the other one is per example compute. And imagine you have a car and you want to go fast. And you have 2 things to control. One is, how much gas or how much you want to push the gas, and the other one is the gear, right? So if you are on 2, and if you want to go faster, there is a limit on how much you can go faster before going to before changing the gear, right? On the other hand, changing the gear to higher one doesn't necessarily give you higher speed if you don't push the gas enough, right? So there is a balance between these 2. And we need to basically be able to somehow find a optimal shifting point. And maybe we need to also do that in machine learning and move from manual models to automatic models that basically they decide about the amount of flops and parameters per example, and then they find a balance between these 2. And I think the idea of AdaTape is a little bit into that direction. So what it does, it says one of the things that we can actually control the computation budget of transformer is the input length. So if the input is longer, we are spending more flops, and if the input is shorter, we are spending less flops. So let's just put the architecture there and not touch it, so we don't make any change to the architecture. What we do instead is that when we are tokenizing the input, we do some processing and we add some dummy tokens. I'm going to call it dummy, but later we're going to notice that these tokens are coming from either the input or from a bank. But the idea is to increase the length when the input is complicated and to decrease it when the input is simple. So basically, you are playing with the computational budget of the model by playing with the input sequence, right? So this elasticity somehow enables the model to have different amount of computation spent on different inputs. And this is actually one of the ideas that makes the adaptive computation like really simple, because you don't need to touch the architecture and you just need to play with the input sequence. And at the end of the day, this pathways idea, which Google is actually working on, which basically is, having a single model that is capable of, basically processing lots of input across, millions of tasks, and having some sort of, control over what part of the model is engaged in processing different inputs is the ultimate goal that we want to move forward by having dynamic and adaptive computation. All right, and the last point is that at the end of the day, one of the most difficult part about this, dynamic computation, is that these models are not easy in terms of implementation. So in many situations, what you end up with is that you implement them, but using the accelerators that we have, like TPU and GPU, you don't see the speed up in practice, right? So you see that, still, and the reason is that, for example, GPUs or TPUs, they love dense matrix multiplications, and every time that you want to sparsify something, or if you want to have some sort of, incomplete operation or partial, multiplications, it just becomes difficult, right? And some situations, like, if you're working with GPUs, you can come up with some sort of ideas to do some custom kernel CUDA implementation, but at the end of the day, it's not always flexible and it's not always possible. For example, on TPUs, it's much harder to do that in XLA. And I think this is one of the probably one of the factors that is stopping us to making great progress in this direction. But I'm hopeful simply because there's no way that we can actually go toward this general intelligence without having models that they spend different amount of compute for different inputs. All right, the last one, the last section that I want to talk about is basically related to recycling. And this is quite new, and this is a concept that basically is somehow, it's new in terms of, becoming a topic of a discussion, but it's not it's a new research direction. There are many research done in this direction about how we can actually do that. But the idea is that imagine a situation that you are in a company or you are in a research lab that you afford to basically train a single giant language model one time. And let's say it is per year, right? So basically you have to spend, I don't know, $5 million on training a GPT-3, and then you understand that this is not the last one that we are doing, right? Every year the technology is different, and we find about different ideas, different optimization techniques to get better language models. But what does it mean? Does it mean that the next year that we have better algorithms and better architectures, we just threw away what we had last year? So we spent $5 million on that, and then what do we do with that? Just threw it away and then train a new one from scratch and spend another $5 million or not? So when we were working with the smaller models, it was just easy, we say that, okay, I'm going to just, throw that away and train something from scratch. But right now, it's not easy because the cost is huge. And this also has, serious environmental impact. So you don't want to do that frequently. And besides the cost, this is not a good idea to basically train a giant model from scratch every year. But there is a big risk on that, which is called ossification. And what does that mean? It means that if you train a model, there is a good way that your model is, there's a good chance that your model is imperfect, right? You did your best, but at the end of the day, there are many issues with any model that you train, right? I mean, if you go try ChatGPT, there are many issues that, still, like, I don't know, you ask ChatGPT which one is bigger, 1 divided by 4 or 1 divided by 3, and sometimes, it just gives you a wrong answer. So such a simple question, but this shows the imperfection of these models. And ossification means that if I have this, so if I kickstart training another model based on this one, is there a guarantee that I won't be as imperfect as is this one or not? So there is a chance that if I start from this model and train another one, all the issues that I have in this model is going to be also in the next one. So you don't want to do that. But on the other hand, you don't want to also start from scratch and hope for something completely new. So there is this trade-off that, what should we do? And is there any recipe that we can somehow make use of the offline compute? So we call it offline compute because this is a compute that you already spent. It's some sort of, a cost sunk cost. And basically, you just want to find a way to make use of that. So there are two things that we need to do. First of all, before thinking about any recipe, every time that you want to train a model, think about, how you can make it reusable, right? Like if I train a model right now, I should think about, okay, next year, there should be a way that I can reuse this model, right? And based on that requirement, you somehow make some design choices. As a really simple example is that when training different models, you can use different learning rate scheduling, right? And if you are using a learning rate scheduling that basically decays the learning rate all the way to 0 based on your number of steps, if you say that, like, I want to train it for 10,000 steps, and you decay the learning rate all the way to 0 at the end of training, it just kind of, at the end of training, you are pushing your model to a really, to a local minima because you're sending a really small update to your model. So you're basically adjusting your model based on a really close neighborhood, and somehow it just somehow ossifies the model. It just gives your model some certainty that this is the best that we can do in the next 1,000 steps, so let's do it. So there's less chance to actually do something better. But imagine a situation that your budget is like for having 4 GPUs for 3 days, and it's like 10K steps, and suddenly the Minister of Education comes to you and say that, okay, here is like $2 more million, so maybe you want to continue the training. And then the issue is that you already trained your model to a situation that is not resumable, right? So basically, you cannot resume the training simply because you decayed your learning rate all the way to 0. So this is somehow, goes against the idea of infinite training and, reusability. So you need to be careful about that. And one of the simple ideas is that, maybe I should use some sort of, a decay or learning scheduler that doesn't go to 0 at the end of training, like similar to this square root, basically this reciprocal square root learning rate decay, or even constant. And then a little bit like, before the last step, you just do a cool down. So you decay to 0. But next time when you want to resume it, you just go back to the point that you wanted to decay and then continue the training. So this is like one of the easy and simple principles to have infinite training. And another direction for recycling, so the first concern is to design models that they are reusable, right? Like don't go for strategies that makes your model, gives you a model that is great for now, but not for future. And the next one is that, okay, so we have these models that they are reusable. How do we reuse them? And what are the ideas? So there are plenty of ideas. 3 of them, I listed them here, basically. Like the first one is grafting. Grafting means that, I have this model, imagine a transformer that has, 12 layers. And next year, I want to train a model, and it's a 24 layers transformer. So what should I do? One idea is that maybe I can, initialize that larger model from this model, and then take these 12 layers and initialize the first one, and then again repeat it on the top 12 one. So basically, you're grafting your new model out of the previous one. Another one is distillation, which is like, everyone uses distillation. So maybe you can always distill a model that you train and into something that is, smaller. And the last one is retrieval based. And again, there are many ideas around this retrieval based. The easy one is that maybe I can use my previous model to retrieve some information for the new model. Or I can maybe even retrieve some of the weights of the previous model to the new model, which this second one is a bit like, how do you do that and how does it work? But still there are ideas around it. So one of the papers that I think it just went out a week ago is sparse upcycling. So it's just like, it's an internship project in our team. So the idea is that imagine a situation that you have a dense model, and you already trained that, and you have it on your table, and you get some budget to continue the training of this model. There are 2 ways. One is, okay, I'm going to just continue training the dense model for, I don't know, like 20% more steps. And another idea, which basically we tried in this paper, is that like upcycling this dense model for training or continue training a sparse model. So it's really simple, because what you need to do is just to simply copy some weights to a sparse model. So if you have a dense transformer, which you have layer norm, attention, layer norm, MLP. So just copy the layer norm weight and attention weight, and again layer norm weight, and this MLP is going to be copied over all the experts that you have here. And then basically you randomly initialize a router or any other weights that is not coming from the dense model, and then you continue the training. So you might say that, okay, what do we expect from this? One expectation is that this dense model, so we basically, if we have a dense, so the assumption was that at the day 1 we have a dense model that is trained, right? So we don't want to train a dense model and a sparse model, because there's a good chance that if you just train a sparse model from scratch, it's going to be better than that. So the assumption is that it's an already trained model, and we want to start from that. And we want to know what is the best strategy to continue the training. So how can we basically upcycle this dense model? And we show that basically by just this simple idea of copying the weights from a dense model to a sparse model, by spending similar amount of compute, you can actually get a much better model by sparsifying an already trained dense model. So this is from the upstream performance on both sparse vision transformer and a sparse T5 in both situations, which one is on vision domain and one is on language. You can see that basically sparsifying the model when initializing from the dense model just gives you a much better model at the end of the 20% extra training. This is also on downstream performance, so similar observation. But like this sparse upcycling was one of the recycling ideas. Another one that we actually found really effective, and I think this is actually one of the coolest things that we've done, is that so we had PALM. PALM is this pass-wave language model, which is 540 billion parameter model, and we already trained it last year. And then there was a discussion at Google that, okay, what should we do? The next move, what is, are we going to train another one? What are the ideas? How we can actually make best use of this offline compute? So one of the things that we worked on last year was basically working on a new objective function for training language models. We call it UL2. And in language modeling, what you do is that you usually, so there are two different ideas. One is that, okay, I do mask language modeling, like T5 or BERT. And the other one is just next word prediction, so autoregressive or causal language modeling. So UL2 says that, instead of doing one, with GPT-3 is actually, causal language modeling, and T5 is like, mass language modeling. So UL2 says that, let's just use a mixture of these objectives and train a model with all these objectives together. And then we realized that in different contexts, this UL2 is going to be a better objective for training language modeling, right? And then, but we already had Palm trained, so this was done after Palm was finished training. So we wanted to know that, okay, what is the situation here? Do we want to train Palm or retrain Palm with this new objective function, or no, we want to somehow find a way to reuse it? And then we tried this simple idea of up-training Palm with this new objective function, and suddenly we got a huge boost in different metrics, while we are adding basically no extra cost. So this is, I think it's not even visible that basically this is Palm, and this is the UL2 repair version of Palm. So it's slightly to the right. The x-axis is the cost, and the y-axis is the quality. So basically, by spending like this tiny amount of extra compute, we got a version of Palm that is as good as the final version of Palm. So we basically show that we could have somehow saved 4.4 million TPU hours by using this one, right? So the idea is that, okay, there are ways that you can up-train a model with better ideas without throwing them out, So the whole idea is how we can recycle something, or how we can basically find a way to use the model that we trained already and make up a new one which is better than the final version of this model. So this UL2 repair actually shows different, superiority over like vanilla Palm. And there are a bunch of tasks. For example, these are from Big Bench, where the language models are somehow semi-random, and suddenly at some scale they start doing something reasonable. And we just show that basically an 8 billion parameter or 62 billion parameter model with UL2 repair is doing as good as a 540 billion parameter model. And sometimes we also see this emergent abilities coming sooner, so on smaller scale, which is also pretty cool, because you don't need to wait up to that huge size to see this amazing abilities out of language models. All right, I think this was somehow my talk. I think there are plenty of time for questions. But I'm happy also to chat about any of these topics after the talk if you're interested.
Thank you, Mustafa, for your great talk. Now we have a Q&A session. So please raise your hand if you have any questions.
Thank you for a great talk, Mustafa. I have many questions, of course. So let me start with number one. So you showed this jungle of long context transformers.
Yeah.
And let me assume I'm a practitioner, and I wanted to use any of those. And unfortunately, most practitioners today actually don't use any of those. So your reaction to this jungle was, I'm inventing a new one. Right? You invented that tape thing on top of the typical scientist's way of dealing with things. But which one would you actually suggest to use if I was a practitioner? And please don't say it depends.
Okay. Well, it's actually a good question. And I get this question a lot, simply because people, when I show them this taxonomy of, different ideas around, making transformer more efficient on long context, they say, okay, they scratch their head and it's okay, so there are 50 different papers, so I should go and read those papers and implement them and see which one is working better for. So I'm really sad that you told me that I should not use the phrase "it depends," because it really depends. but if I want to, so
But let's say, well, I'll make it easier for you because you're right. That was mean from me. But make it easier. Let's say we want a few-shot learner for GPT-3 with a context size of 8,000. Which one would you use?
As a matter of fact, we actually started from this example, that what if you want to summarize a book, right? Like, you want to fit a book to the model and then get a summary out of it. So now which one do you use? I would go for, so you don't see the taxonomy. It's actually in front of me. I don't know if it's possible. I can, project this screen to the, project this slide to the screen. But I personally prefer two groups out of these 5, 6 groups. This one is memory and downsampling. And I want to talk about memory a little bit. And the other one is basically local global attention. So these two are those that I put my money on it, right? Like, the first one is memory. And one thing that I think is somehow effective is that basically we need to have models that they are somehow augmented by some sort of retrieval mechanism where they retrieve part of the input that they need to process instead of actually, and when I'm talking about retrieval or memory, I'm not talking about an external knowledge base or external, database. I'm talking about actually the input. So retrieving part of the input, or dealing with the input as different as a memory that I need to access. So this is actually one thing that I would go for. And in general, I strongly believe in retrieval augmented models. I think it's a bit like insane to always depend on parameters, and we need to basically find a way for enabling model to have access to something outside the model itself. And the other one that I saw actually a lot of good result out of it is that basically this local global. So we have some, out of these transformer models, I actually worked with a lot of them in different contexts, especially on video. And those that they have some sort of factorization of the process on local neighborhood and then globally but unrepresentative of these neighborhoods, they are also doing pretty good. So this local global is something that is both efficient and it's also a really good inductive bias, simply because in most modalities that we work with, neighborhood and locality has some sort of meaning. So if you somehow process the input with respect to the neighborhood of it, it just gives you some sort of inductive bias that is also good for your task, but also brings some efficiency. So these two are those that I would just go without providing any context, like memory and local global. But again, you might find an application that, I don't know, so for example, like learnable pattern is a better idea, or low rank might be a better idea.
Thank you. You're actually missing memoizing transformers on there, but I think they're probably newer than this paper was, right?
Which one?
Memoizing transformers, which is exactly doing that.
I think it probably
appeared later,
came up, after we published this survey. We are trying to keep this alive, and hopefully we can actually update this taxonomy and add papers to it.
Yeah. Any more questions?
I'm Rangyong from KAIST, and thanks for the great talk. I have a question about the efficient ML. You've mentioned that it is the best to conduct comparison for whole matrix, like model parameters, example for seconds, for choosing efficient ML model. But it sounds like too general for me. So, is there any specific interest or favor particular matrix that Google cares most about for ML inference and training, respectively?
Okay, so your question is that when we're talking about cost of inference and training, which one is important? Is that your question, or?
I mean, the specific matrix that Google cares about most, for respectively for training, ML training and ML inference. Like, for example, it's like examples per second for ML inference, or model parameters for ML training, like this.
Got it. Okay. So what you're saying is that basically we have these different cost metrics: flops, number of parameters, and speed, and example per train, like or example per second or something. which one is important for inference and which one is important for training, right?
Yes.
Okay, so it's a bit, okay, so what I want to say, again, I know every time that someone asks a question, I want to just immediately use by, like, saying that it depends, but, yeah, I try my best to avoid that, but if you want to actually, I would say, let's just see which one would translate better.
Yeah, so let me change my question a bit
Yeah.
different. Like, I know that Google cares most to minimizing TCO within proper quality of service, but which metric usually affects TCO most among the metric that you mentioned in your slide?
Okay, so I think one of the things that we probably care about is that of course when you go to applications, and inference latency or some sort of speed is the most important, right? Because it just immediately impacts user experience, right? If on your phone, if you ask some questions and then you get an answer in like a fraction of a second, but it's not an amazing answer, probably it's more satisfying to you than getting an answer which is amazing but half an hour later, right? So this is absolutely one of the things that is important. But for training, I think at the end of the day, it just goes to money, right? Like, if I want to minimize the cost of training, right? And then I'm spending money on training these different models. And maybe at the end of the day, I don't care how much flops or parameters or no. What I want to know is that how can I maximize the quality of my model by spending less money on it. And again, I think it also has direct relation with carbon footprint and those things. But I think those like flops or number of parameters or speed, these are a little bit like more scientific type of metrics. Some of them would translate really well onto the cost, and by cost I mean like the monetary cost. But some of them are not. Like flops is, for example, it's a bit off. I mean, like I would say no one really talks about flops when we talk about, or we actually talk about total training flops where we are actually comparing different models. But at the end of the day, most of the time, you can also check that in Google papers that we really have total training TPU days on the x-axis, which is basically a really good indicator of how much money we're firing for training this model.
Yeah, we have time for last.
So if we still have time for one question where you may not answer, it depends. So Palm, the Pathways language model.
Yes.
So when I read the paper, I mean, I know I have one of the authors, that's why I'd like you to tell the story. When I read the paper, I was actually missing the pathways in the Pathways language model because there is no conditional computation in the model. It's basically just a standard transformer, and I was quite shocked. And then the last paragraph kind of says, well, we'll do this later. Exactly, what you're showing is not at all in the Pathways language model. So can you maybe shed some light on this? I was shocked when I read it.
Okay, so let me tell you what's going on. I know, it's like from outside, it's like, okay, what's going on? But this is not Pathways that Jeff talked about, So, so the idea is that, so we had also poly, and we had, party. So these are like, pathways image generation or pathways language image understanding. So what is happening right now is that we are publishing components independently, and hopefully you'll see some, some papers or some new demo or something that all these come together, and then hopefully this happens. But to answer your question, Paul, so like if I want to share a little bit, like at least there's a huge infrastructure is going to be like built for these pathways, right? And then so people are working on it, but also we are trying to basically stress test this infrastructure in different contexts. One of them is that what if we just use this infrastructure in the context of training a language model and forget about other tasks and sparsity and everything? And I think there are a lot of engineering. So like Palm actually uses the infrastructure from Pathways to train. So this is one of the main connection. But on the other hand, what is happening is that basically many Pathways papers are coming out, and these are about individual components. But the target and the goal is to hopefully soon put all of them together and then get something out. But there are going to be a lot of cool stuff, and soon we're going to see a lot of good stuff. But I agree, it's a bit like what I didn't expect, like pathways language model. This is not.
Yeah. So in other words, it's using the pathways language infrastructure, and it's only one path.
Yes.
Okay,
so it's for now. This paper is about one path, and another, like, poly is another path. But hopefully these are different pieces of a puzzle, and then we can put them and present them as a single image soon.
Thank you.
Yeah.
Okay. Thank you, Mustafa, again for your talk again. This is the last talk of this session, Track A Efficient AI. So thank you very much for all speakers and our offline and online audience. So now we are done. So keynote presentations will start from 3:30 in 30 minutes, and please continue to watch. Thank you very much.